Quantum computing has several top players like superconductors, trapped ions, and neutral atoms. But photonic quantum computing might be catching up, especially PsiQuantum, who is the highest valued quantum computing company in the world right now. Since their $3 billion valuation, they recently raised close to $1 billion investment from the Australian government.
With so many eyes on this investment, we decided to turn to their recent arXiv preprint and understand their tech. Because at Quantum News Monthly, we get more excited about big inventions, not big valuations. Photonic quantum computing uses photons as qubits, and PsiQuantum's approach has some big advantages, but also some serious challenges. Their claim to fame can be summarized in this line from the paper: the first realization of an integrated photonic technology platform capable of on-chip generation, manipulation, and detection of photonic qubits.
But what does this mean? That's what we'll look into today. We'll explain how photonic quantum computing works, how PsiQuantum tackles the unique challenges of integrated photonics, and what remains to be solved. Watch till the end to find out 2 challenges that PsiQuantum must still overcome to come out on top.
Disclaimer: this paper is not peer-reviewed yet, so some of the content may change. PsiQuantum uses photons as qubits, which allows universal, fault-tolerant quantum computing using basically only 4 ingredients: beam splitters, phase shifters, single photon sources, and photon detectors. These are pretty fundamental instruments for any kind of optics experiment. And with these components, you can do all these quantum operations like state preparation, measurement, grading interference, and fusion.
People originally thought that it is impossible to do quantum computing with photons because photons don't really interact with each other. An interaction is necessary for entangling gates. However, Kayal, Laflamme, and Milburn found a way. The idea is that by using extra photons, you can do entangling gates on your qubits conditional to measuring the extra photons at a certain desired result. So you can make a 2-qubit gate that works only with a certain probability. This is an example of a controlled Z-gate that works with probability 1/16.
Gates that work probabilistically sound really inefficient. Imagine that your computer can do 1 plus 1 correctly 1/16th of the time. It can do 1 plus 1 plus 1 correctly with probability 1/16th squared, which is 1/256. What can we even do with this?
You see, the intuitive way to compute something is to start with a bunch of 0 bits and do a bunch of gates that give the instruction for computing something. That's gate-based quantum computing, and it's pursued by other quantum technology platforms. But turns out, there's a whole other way of doing this. Instead of starting with qubits in the 0 state, you start with a huge cluster of entangled qubits. And instead of doing gates, you measure qubits in the right order and right basis, chipping off the cluster state little by little. In the very end, you get the quantum computing results that you want. This is called measurement-based quantum computing.
So instead of entangling the qubits using gates, you prepare all the entanglement before the computation even begins, and the computation is done by just easy measurements. And this paradigm works really well with photons. So in this cluster state, the circles are photons and these edges represent entanglement.
Okay, sounds fancy, but how are we even going to make the huge cluster state? Fortunately, preparing a certain state is much easier than performing gates. We still have the limitation that entanglement works probabilistically, so some photons will be wasted, and the question is how many photons are needed to make a huge cluster state. This is where tremendous progress has been made throughout the past 2 decades. Physicists have developed ingenious ideas like fusion to make cluster states using as few photons as possible.
And with a 3-dimensional cluster state, you can do error correction and therefore fault-tolerant quantum computing. This is the direction PsiQuantum is pushing, making a huge 3D cluster state using millions of photons and then doing a bunch of measurements, which eventually give you the quantum computing results fault-tolerantly. By the way, you can watch our previous videos on error correction and fault tolerance.
What sets PsiQuantum apart from other photonics players is their fully integrated silicon photonics, as in all the components are on silicon chips. This is how a photonic setup used to look, and still do in most academic labs. Tabletop experiments like this are impressive for science, but scaling this to millions of components will take up too much real estate. The Canadian company Xanadu has also shown on-chip photonics for quantum computing. But PsiQuantum partnered with GlobalFoundries, a state-of-the-art semiconductor manufacturer, to integrate all their device components on chip. This includes single photon sources, filters, interferometers, single photon detectors, and phase shifters.
Some other cool features are that 1. Their circuits are reconfigurable using interferometers and phase shifters. 2. The chips can be connected to fiber networks and to each other via fibers because of their efficient fiber-to-chip coupling. And 3, they have the world's first fully integrated heralded single photon source, where heralding is a way to generate single photons and also know the time when they're generated.
The last impressive thing we want to talk about before we have to start grilling them is their fidelities. Because they don't work like other quantum computers, they don't have the typical single and 2 qubit gates. But all their operations have multiple nines of fidelities, which is great. There's span fidelity, which is how accurately you can create the right qubit states and detect them correctly, is almost 4 nines, if you ignore this huge asterisk here. And the closest thing to a 2 qubit gate would be their measurement of the bell fidelity, which is higher than 99%, which is also a great start.
However, what we cannot ignore is that big asterisk, which is photon loss. The authors explain that silicon waveguides incur high photon loss, which is basically saying that their qubits are leaking out of the tunnels they've designed for them. PsiQuantum has improved their photon loss over the years, and they have some ideas for how to keep improving them, namely silicon nitride waveguides, which have lower loss than silicon waveguides.
And the second challenge that probably still needs work is their single photon generation. As the authors explain, photons must be generated with high efficiency, well-defined timing, and a high repetition rate, while also being spectrally pure and indistinguishable. But the quality of photon generation remains a challenge. PsiQuantum's Clich coefficiency is 26%, where Clich coefficiency is a measure of how well-timed and reliable this single photon generation is. But to PsiQuantum's credit, this efficiency is better than many, and they have managed to integrate their photon sources on the same chip.
So of course, PsiQuantum has some formidable technical challenges ahead of them, but it's refreshing to see their tremendous progress in integrating photonics on chip and showing all the ingredients for photonic quantum computing.
It will be exciting to see how PsiQuantum scales up these devices to deliver on their promise of making useful quantum computers. We put in a lot of time researching and presenting these video reviews, so if you enjoyed this, please consider subscribing and sharing with your friends.
None of us make a dime from these videos, not even our friends who do video and graphics editing behind the scenes. We volunteer our time because we're truly passionate about quantum science and want to foster nice discussions around this exciting field. So your likes, comments, shares, they truly mean a lot.
Thank you, and see you in the next one.